Keel effect and weight distribution. A high-wing aircraft always has the tendency to turn the longitudinal axis of the aircraft into the relative wind, which is often referred to as the keel effect. These aircraft are laterally stable simply because the wings are attached in a high position on the fuselage, making the fuselage behave like a keel, exerting a steadying influence on the aircraft laterally about the longitudinal axis. When a high-winged aircraft is disturbed and one wing dips, the fuselage weight acts like a pendulum, returning the aircraft to the horizontal level. Laterally stable aircraft are constructed so that the greater portion of the keel area is above the CG. Figure 5.31. Thus, when the aircraft slips to one side, the combination of the aircraft's weight and the pressure of the airflow against the upper portion of the keel area, both acting about the CG, tends to roll the aircraft back to wings level flight. End of page 5 to 18. Directional stability, yawing. Stability about the aircraft's vertical axis, the sideways moment, is called yawing or directional stability. Yawing or directional stability is the most easily achieved stability in aircraft design. The area of the vertical fin and the sides of the fuselage aft of the CG are the prime contributors that make the aircraft act like the well-known weather vane or arrow, pointing its nose into the relative wind. In examining a weather vane, it can be seen that if exactly the same amount of surface were exposed to the wind in front of the pivot point as behind it, the forces fore and aft would be in balance and little or no directional movement would result. Consequently, it is necessary to have a greater surface aft of the pivot point than forward of it. Similarly, the aircraft designer must ensure positive directional stability by making the side surface greater aft than ahead of the CG. Figure 5.32. To provide additional positive stability to that provided by the fuselage, a vertical fin is added. The fin acts similar to the feather on an arrow when maintaining straight flight. Like the weather vane and the arrow, the farther aft this fin is placed and the larger its size, the greater the aircraft's directional stability. If an aircraft is flying in a straight line, and a sideward gust of air gives the aircraft a slight rotation about its vertical axis, i.e., the right, the motion is retarded and stopped by the fin because while the aircraft is rotating to the right, the air is striking the left side of the fin at an angle. This causes pressure on the left side of the fin, which resists the turning motion and slows down the aircraft's yaw. In doing so, it acts somewhat like the weather vane by turning the aircraft into the relative wind. The initial change in direction of the aircraft's flight path is generally slightly behind its change of heading. Therefore, after a slight yawing of the aircraft to the right, there is a brief moment when the aircraft is still moving along its original path, but its longitudinal axis is pointed slightly to the right. The aircraft is then momentarily skidding sideways and, during that moment, since it is assumed that although the yawing motion has stopped, the excess pressure on the left side of the fin still persists, there is necessarily a tendency for the aircraft to be turned partially back to the left. That is, there is a momentary restoring tendency caused by the fin. This restoring tendency is relatively slow in developing and ceases when the aircraft stops skidding. When it ceases, the aircraft is flying in a direction slightly different from the original direction. In other words, it will not return of its own accord to the original heading. The pilot must re-establish the initial heading. A minor improvement of directional stability may be obtained through sweepback. Sweepback is incorporated in the design of the wing primarily to delay the onset of compressibility during high-speed flight. In lighter and slower aircraft, sweepback aids in locating the center of pressure in the correct relationship with the CG. A longitudinally stable aircraft is built with the center of pressure aft of the CG. Because of structural reasons, aircraft designers sometimes cannot attach the wings to the fuselage at the exact desired point. End of page 5 to 19. If they had to mount the wings too far forward, and at right angles to the fuselage, the center of pressure would not be far enough to the rear to result in the desired amount of longitudinal stability. By building sweepback into the wings, however, the designers can move the center of pressure toward the rear. The amount of sweepback and the position of the wings then place the center of pressure in the correct location. When turbulence or rudder application causes the aircraft to yaw to one side, the opposite wing presents a longer leading edge perpendicular to the relative airflow. The airspeed of the forward wing increases and it acquires more drag than the back wing. The additional drag on the forward wing pulls the wing back, turning the aircraft back to its original path. The contribution of the wing to static directional stability is usually small. The swept wing provides a stable contribution depending on the amount of sweepback, but the contribution is relatively small when compared with other components. Free directional oscillations, Dutch roll. Dutch roll is a coupled lateral/directional oscillation that is usually dynamically stable but is unsafe in an aircraft because of the oscillatory nature. The damping of the oscillatory mode may be weak or strong depending on the properties of the particular aircraft. If the aircraft has a right wing pushed down, the positive side slip angle corrects the wing laterally before the nose is realigned with the relative wind. As the wing corrects the position, a lateral directional oscillation can occur resulting in the nose of the aircraft making a figure 8 on the horizon as a result of two oscillations, roll and yaw, which, although of about the same magnitude, are out of phase with each other. In most modern aircraft, except high-speed swept wing designs, these free directional oscillations usually die out automatically in very few cycles unless the air continues to be gusty or turbulent. Those aircraft with continuing Dutch roll tendencies are usually equipped with Euro-stabilized yaw dampers. Manufacturers try to reach a midpoint between too much and too little directional stability. Because it is more desirable for the aircraft to have spiral instability than Dutch roll tendencies, most aircraft are designed with that characteristic. Spiral instability. Spiral instability exists when the static directional stability of the aircraft is very strong as compared to the effect of its dihedral in maintaining lateral equilibrium. When the lateral equilibrium of the aircraft is disturbed by a gust of air and a side slip is introduced, the strong directional stability tends to yaw the nose into the resultant relative wind while the comparatively weak dihedral lags in restoring the lateral balance. Due to this yaw, the wing on the outside of the turning moment travels forward faster than the inside wing and, as a consequence, its lift becomes greater. This produces an overbanking tendency which, if not corrected by the pilot, results in the bank angle becoming steeper and steeper. At the same time, the strong directional stability that yaws the aircraft into the relative wind is actually forcing the nose to a lower pitch attitude. A slow downward spiral begins which, if not counteracted by the pilot, gradually increases into a steep spiral dive. Usually the rate of divergence in the spiral motion is so gradual the pilot can control the tendency without any difficulty. Many aircraft are affected to some degree by this characteristic, although they may be inherently stable in all other normal parameters. This tendency explains why an aircraft cannot be flown hands-off indefinitely. Much research has gone into the development of control devices, wing leveler, to correct or eliminate this instability. The pilot must be careful in application of recovery controls during advanced stages of this spiral condition or excessive loads may be imposed on the structure. Improper recovery from spiral instability leading to in-flight structural failures has probably contributed to more fatalities in general aviation aircraft than any other factor. Since the airspeed in the spiral condition builds up rapidly, the application of back elevator force to reduce the speed and to pull the nose up only tightens the turn, increasing the load factor. The results of the prolonged uncontrolled spiral are in-flight structural failure, crashing into the ground, or both. Common recorded causes for pilots who get into this situation are loss of horizon reference, inability to control the aircraft by reference to instruments, or a combination of both. Effect of wing planform. Understanding the effects of different wing planforms is important when learning about wing performance and airplane flight characteristics. A planform is the shape of the wing as viewed from directly above and deals with airflow in 3 dimensions. Aspect ratio, taper ratio, and sweepback are factors in planform design that are very important to the overall aerodynamic characteristic of a wing. Figure 5.33. Aspect ratio is the ratio of wingspan to wing chord. Taper ratio can be either in planform or thickness, or both. In its simplest terms, it is a decrease from wing root to wingtip in wing chord or wing thickness. Sweepback is the rearward slant of a wing, horizontal tail, or other airfoil surface. There are 2 general means by which the designer can change the planform of a wing, and both will affect the aerodynamic characteristics of the wing. End of page 5 to 20. The first is to effect a change in the aspect ratio. Aspect ratio is the primary factor in determining the 3-dimensional characteristics of the ordinary wing and its lift/drag ratio. An increase in aspect ratio with constant velocity will decrease the drag, especially at high angles of attack, improving the performance of the wing when in a climbing attitude. A decrease in aspect ratio will give a corresponding increase in drag. It should be noted, however, that with an increase in aspect ratio there is an increase in the length of span, with a corresponding increase in the weight of the wing structure, which means the wing must be heavier to carry the same load. For this reason, part of the gain, due to a decrease in drag, is lost because of the increased weight, and a compromise in design is necessary to obtain the best results from these two conflicting conditions. End of page 5 to 21. The second means of changing the planform is by tapering, decreasing the length of chord from the root to the tip of the wing. In general, tapering causes a decrease in drag, most effective at high speeds, and an increase in lift. There is also a structural benefit due to a saving in weight of the wing. Most training and general aviation type airplanes are operated at high coefficients of lift, and therefore require comparatively high aspect ratios. Airplanes that are developed to operate at very high speeds demand greater aerodynamic cleanness and greater strength, which require low aspect ratios. Very low aspect ratios result in high wing loadings and high stall speeds. When sweepback is combined with low aspect ratio, it results in flying qualities very different from a more conventional high aspect ratio airplane configuration. Such airplanes require very precise and professional flying techniques, especially at slow speeds, while airplanes with a high aspect ratio are usually more forgiving of improper pilot techniques. The elliptical wing is the ideal subsonic planform since it provides for a minimum of induced drag for a given aspect ratio, though as we shall see, its stall characteristics in some respects are inferior to the rectangular wing. It is also comparatively difficult to construct. The tapered airfoil is desirable from the standpoint of weight and stiffness, but again is not as efficient aerodynamically as the elliptical wing. In order to preserve the aerodynamic efficiency of the elliptical wing, rectangular and tapered wings are sometimes tailored through use of wing twist and variation in airfoil sections until they provide as nearly as possible the elliptical wing's lift distribution. While it is true that the elliptical wing provides the best coefficients of lift before reaching an incipient stall, it gives little advance warning of a complete stall, and lateral control may be difficult because of poor aileron effectiveness. In comparison, the rectangular wing has a tendency to stall first at the wing root and provides adequate stall warning, adequate aileron effectiveness, and is usually quite stable. It is, therefore, favored in the design of low-cost, low-speed airplanes. Aerodynamic forces in flight maneuvers. Forces in turns. If an aircraft were viewed in straight and level flight from the front, Figure 5.34, and if the forces acting on the aircraft could be seen, lift and weight would be apparent, two forces. If the aircraft were in a bank, it would be apparent that lift did not act directly opposite to the weight, rather it now acts in the direction of the bank. A basic truth about turns is that when the aircraft banks, lift acts inward toward the center of the turn, perpendicular to the lateral axis as well as upward. Newton's first law of motion, the law of inertia, states that an object at rest or moving in a straight line remains at rest or continues to move in a straight line until acted on by some other force. An aircraft, like any moving object, requires a sideward force to make it turn. In a normal turn, this force is supplied by banking the aircraft so that lift is exerted inward, as well as upward. The force of lift during a turn is separated into two components at right angles to each other. One component, which acts vertically and opposite to the weight, gravity, is called the vertical component of lift. The other, which acts horizontally toward the center of the turn, is called the horizontal component of lift or centripetal force. The horizontal component of lift is the force that pulls the aircraft from a straight flight path to make it turn. Centrifugal force is the equal and opposite reaction of the aircraft to the change in direction and acts equal and opposite to the horizontal component of lift. This explains why, in a correctly executed turn, the force that turns the aircraft is not supplied by the rudder. The rudder is used to correct any deviation between the straight track of the nose and tail of the aircraft into the relative wind. A good turn is one in which the nose and tail of the aircraft track along the same path. End of page 5 to 22. If no rudder is used in a turn, the nose of the aircraft yaws to the outside of the turn. The rudder is used rolling into the turn to bring the nose back in line with the relative wind. Once in the turn, the rudder should not be needed. An aircraft is not steered like a boat or an automobile. In order for an aircraft to turn, it must be banked. If it is not banked, there is no force available to cause it to deviate from a straight flight path. Conversely, when an aircraft is banked, it turns provided it is not slipping to the inside of the turn. Good directional control is based on the fact that the aircraft attempts to turn whenever it is banked. Pilots should keep this fact in mind when attempting to hold the aircraft in straight and level flight. Merely banking the aircraft into a turn produces no change in the total amount of lift developed. Since the lift during the bank is divided into vertical and horizontal components, the amount of lift opposing gravity in supporting the aircraft's weight is reduced. Consequently, the aircraft loses altitude unless additional lift is created. This is done by increasing the AOA until the vertical component of lift is again equal to the weight. Since the vertical component of lift decreases as the bank angle increases, the AOA must be progressively increased to produce sufficient vertical lift to support the aircraft's weight. An important fact for pilots to remember when making constant altitude turns is that the vertical component of lift must be equal to the weight to maintain altitude. At a given airspeed, the rate at which an aircraft turns depends upon the magnitude of the horizontal component of lift. It is found that the horizontal component of lift is proportional to the angle of bank, that is, it increases or decreases respectively as the angle of bank increases or decreases. As the angle of bank is increased, the horizontal component of lift increases, thereby increasing the rate of turn, ROT. Consequently, at any given airspeed, the ROT can be controlled by adjusting the angle of bank. To provide a vertical component of lift sufficient to hold altitude in a level turn, an increase in the AOA is required. Since the drag of the airfoil is directly proportional to its AOA, induced drag increases as the lift is increased. This, in turn, causes a loss of airspeed in proportion to the angle of bank. A small angle of bank results in a small reduction in airspeed, while a large angle of bank results in a large reduction in airspeed. Additional thrust, power, must be applied to prevent a reduction in airspeed in level turns. The required amount of additional thrust is proportional to the angle of bank. To compensate for added lift, which would result if the airspeed were increased during a turn, the AOA must be decreased, or the angle of bank increased, if a constant altitude is to be maintained. If the angle of bank is held constant and the AOA decreased, the ROT decreases. In order to maintain a constant ROT as the airspeed is increased, the AOA must remain constant and the angle of bank increased. An increase in airspeed results in an increase of the turn radius, and centrifugal force is directly proportional to the radius of the turn. In a correctly executed turn, the horizontal component of lift must be exactly equal and opposite to the centrifugal force. As the airspeed is increased in a constant rate level turn, the radius of the turn increases. This increase in the radius of turn causes an increase in the centrifugal force, which must be balanced by an increase in the horizontal component of lift, which can only be increased by increasing the angle of bank. In a slipping turn, the aircraft is not turning at the rate appropriate to the bank being used, since the aircraft is yawed toward the outside of the turning flight path. The aircraft is banked too much for the ROT, so the horizontal lift component is greater than the centrifugal force. Figure 5.35. Equilibrium between the horizontal lift component and centrifugal force is re-established by either decreasing the bank, increasing the ROT, or a combination of the two changes. A skidding turn results from an excess of centrifugal force over the horizontal lift component, pulling the aircraft toward the outside of the turn. The ROT is too great for the angle of bank. Correction of a skidding turn thus involves a reduction in the ROT, an increase in bank, or a combination of the two changes. To maintain a given ROT, the angle of bank must be varied with the airspeed. This becomes particularly important in high-speed aircraft. For instance, at 400 miles per hour mph, an aircraft must be banked approximately 44 degrees to execute a standard rate turn, 3 degrees per second. At this angle of bank, only about 79% of the lift of the aircraft comprises the vertical component of the lift. This causes a loss of altitude unless the AOA is increased sufficiently to compensate for the loss of vertical lift. Forces in climbs. For all practical purposes, the wing's lift in a steady-state normal climb is the same as it is in a steady level flight at the same airspeed. Although the aircraft's flight path changed when the climb was established, the AOA of the wing with respect to the inclined flight path reverts to practically the same values, as does the lift. There is an initial momentary change as shown in Figure 5.36. During the transition from straight and level flight to a climb, a change in lift occurs when back elevator pressure is first applied. Raising the aircraft's nose increases the AOA and momentarily increases the lift. End of page 5 to 23. Lift at this moment is now greater than weight and starts the aircraft climbing. After the flight path is stabilized on the upward incline, the AOA and lift again revert to about the level flight values. If the climb is entered with no change in power setting, the airspeed gradually diminishes because the thrust required to maintain a given airspeed in level flight is insufficient to maintain the same airspeed in a climb. When the flight path is inclined upward, a component of the aircraft's weight acts in the same direction as, and parallel to, the total drag of the aircraft, thereby increasing the total effective drag. Consequently, the total effective drag is greater than the power, and the airspeed decreases. The reduction in airspeed gradually results in a corresponding decrease in drag until the total drag, including the component of weight acting in the same direction, equals the thrust. Figure 5.37. Due to momentum, the change in airspeed is gradual, varying considerably with differences in aircraft size, weight, total drag, and other factors. Consequently, the total effective drag is greater than the thrust, and the airspeed decreases. Generally, the forces of thrust in drag and lift in weight again become balanced when the airspeed stabilizes but at a value lower than in straight and level flight at the same power setting. Since the aircraft's weight is acting not only downward but rearward with drag while in a climb, additional power is required to maintain the same airspeed as in level flight. The amount of power depends on the angle of climb. When the climb is established steep enough that there is insufficient power available, a slower speed results. The thrust required for a stabilized climb equals drag plus a percentage of weight dependent on the angle of climb. For example, a 10 degrees climb would require thrust to equal drag plus 17% of weight. To climb straight up would require thrust to equal all of weight and drag. Therefore, the angle of climb for climb performance is dependent on the amount of excess thrust available to overcome a portion of weight. Note that aircraft are able to sustain a climb due to excess thrust. When the excess thrust is gone, the aircraft is no longer able to climb. At this point, the aircraft has reached its absolute ceiling. Forces in descents. As in climbs, the forces that act on the aircraft go through definite changes when a descent is entered from straight and level flight. For the following example, the aircraft is descending at the same power as used in straight and level flight. End of page 5 to 24. As forward pressure is applied to the control yoke to initiate the descent, the AOA is decreased momentarily. Initially, the momentum of the aircraft causes the aircraft to briefly continue along the same flight path. For this instant, the AOA decreases, causing the total lift to decrease. With weight now being greater than lift, the aircraft begins to descend. At the same time, the flight path goes from level to a descending flight path. Do not confuse a reduction in lift with the inability to generate sufficient lift to maintain level flight. The flight path is being manipulated with available thrust in reserve and with the elevator. To descend at the same airspeed as used in straight and level flight, the power must be reduced as the descent is entered. Entering the descent, the component of weight acting forward along the flight path increases as the angle of descent increases, and, conversely, when leveling off, the component of weight acting along the flight path decreases as the angle of descent decreases. Stalls. An aircraft stall results from a rapid decrease in lift caused by the separation of airflow from the wing surface brought on by exceeding the critical AOA. A stall can occur at any pitch attitude or airspeed. Stalls are one of the most misunderstood areas of aerodynamics because pilots often believe an airfoil stops producing lift when it stalls. In a stall, the wing does not totally stop producing lift. Rather, it cannot generate adequate lift to sustain level flight. Since the CL increases with an increase in AOA, at some point the CL peaks and then begins to drop off. This peak is called the CL max. The amount of lift the wing produces drops dramatically after exceeding the CL max or critical AOA, but as stated above, it does not completely stop producing lift. In most straight-wing aircraft, the wing is designed to stall the wing root first. The wing root reaches its critical AOA first, making the stall progress outward toward the wingtip. By having the wing root stall first, aileron effectiveness is maintained at the wingtips, maintaining controllability of the aircraft. Various design methods are used to achieve the stalling of the wing root first. In one design, the wing is twisted TOA higher AOA at the wing root. Installing stall strips on the first 20 to 25% of the wing's leading edge is another method to introduce a stall prematurely. The wing never completely stops producing lift in a stalled condition. If it did, the aircraft would fall to the earth. Most training aircraft are designed for the nose of the aircraft to drop during a stall, reducing the AOA and unstalling the wing. The nose-down tendency is due to the CL being aft of the CG. The CG range is very important when it comes to stall recovery characteristics. If an aircraft is allowed to be operated outside of the CG range, the pilot may have difficulty recovering from a stall. The most critical CG violation would occur when operating with a CG that exceeds the rear limit. In this situation, a pilot may not be able to generate sufficient force with the elevator to counteract the excess weight aft of the CG. Without the ability to decrease the AOA, the aircraft continues in a stalled condition until it contacts the ground. The stalling speed of a particular aircraft is not a fixed value for all flight situations, but a given aircraft always stalls at the same AOA regardless of airspeed, weight, load factor, or density altitude. Each aircraft has a particular AOA where the airflow separates from the upper surface of the wing and the stall occurs. This critical AOA varies from approximately 16 degrees to 20 degrees depending on the aircraft's design. But each aircraft has only one specific AOA where the stall occurs. There are three flight situations in which the critical AOA is most frequently exceeded: low speed, high speed, and turning. One way the aircraft can be stalled in straight and level flight by flying too slowly. As the airspeed decreases, the AOA must be increased to retain the lift required for maintaining altitude. The lower the airspeed becomes, the more the AOA must be increased. Eventually, an AOA is reached that results in the wing not producing enough lift to support the aircraft, which then starts settling. If the airspeed is reduced further, the aircraft stalls because the AOA has exceeded the critical angle and the airflow over the wing is disrupted. Low speed is not necessary to produce a stall. The wing can be brought into an excessive AOA at any speed. For example, an aircraft is in a dive with an airspeed of 100 knots when the pilot pulls back sharply on the elevator control. Figure 5.38. Gravity and centrifugal force prevent an immediate alteration of the flight path, but the aircraft's AOA changes abruptly from quite low to very high. Since the flight path of the aircraft in relation to the oncoming air determines the direction of the relative wind, the AOA is suddenly increased, and the aircraft would reach the stalling angle at a speed much greater than the normal stall speed. The stalling speed of an aircraft is also higher in a level turn than in straight and level flight. Figure 5.39. Centrifugal force is added to the aircraft's weight and the wing must produce sufficient additional lift to counterbalance the load imposed by the combination of centrifugal force and weight. In a turn, the necessary additional lift is acquired by applying back pressure to the elevator control. This increases the wing's AOA and results in increased lift. End of page 5-25. The AOA must increase as the bank angle increases to counteract the increasing load caused by centrifugal force. If at any time during a turn the AOA becomes excessive, the aircraft stalls. At this point, the action of the aircraft during a stall should be examined. To balance the aircraft aerodynamically, the CL is normally located aft of the CG. Although this makes the aircraft inherently nose-heavy, downwash on the horizontal stabilizer counteracts this condition. At the point of stall, when the upward force of the wing's lift diminishes below that required for sustained flight and the downward tail force decreases to a point of ineffectiveness, or causes it to have an upward force, an unbalanced condition exists. This causes the aircraft to pitch down abruptly, rotating about its CG. During this nose-down attitude, the AOA decreases and the airspeed again increases. The smooth flow of air over the wing begins again, lift returns, and the aircraft begins to fly again. Considerable altitude may be lost before this cycle is complete. Airfoil shape and degradation of that shape must also be considered in a discussion of stalls. For example, if ice, snow, and frost are allowed to accumulate on the surface of an aircraft, the smooth airflow over the wing is disrupted. This causes the boundary layer to separate at an AOA lower than that of the critical angle. Lift is greatly reduced, altering expected aircraft performance. If ice is allowed to accumulate on the aircraft during flight, the weight of the aircraft is increased while the ability to generate lift is decreased. Figure 5.40. As little as 0.8 mm of ice on the upper wing surface increases drag and reduces aircraft lift by 25%. Pilots can encounter icing in any season, anywhere in the country, at altitudes of up to 18,000 feet and sometimes higher. Small aircraft, including commuter planes, are most vulnerable because they fly at lower altitudes where ice is more prevalent. They also lack mechanisms common on jet aircraft that prevent ice buildup by heating the front edges of wings. Icing can occur in clouds anytime the temperature drops below freezing and supercooled droplets build up on an aircraft and freeze. Supercooled droplets are still liquid even though the temperature is below 32 degrees Fahrenheit, F, or 0 degrees Celsius, C. Angle of attack indicators. The FAA, along with the General Aviation Joint Steering Committee, GAJSC, is promoting AOA indicators as one of the many safety initiatives aimed at reducing the general aviation accident rate. AOA indicators will specifically target loss of control, accidents. Loss of control is the #1 root cause of fatalities in both general aviation and commercial aviation. More than 25% of general aviation fatal accidents occur during the maneuvering phase of flight. Of those accidents, half involve stall/spin scenarios. Technology such as AOA indicators can have a tremendous impact on reversing this trend and are increasingly affordable for general aviation airplanes. Figure 5.41. The purpose of an AOA indicator is to give the pilot better situation awareness pertaining to the aerodynamic health of the airfoil. End of page 5-26. This can also be referred to as stall margin awareness. More simply explained, it is the margin that exists between the current AOA that the airfoil is operating at and the AOA at which the airfoil will stall, critical AOA. Angle of attack is taught to student pilots as theory in ground training. When beginning flight training, students typically rely solely on airspeed and the published 1g stall speed to avoid stalls. This creates problems since this speed is only valid when the following conditions are met. 1. Unaccelerated flight, a 1g load factor. 2. Coordinated flight, inclinometer centered. 3. At one weight, typically maximum gross weight. Speed by itself is not a reliable parameter to avoid a stall. An airplane can stall at any speed. Angle of attack is a better parameter to use to avoid a stall. For a given configuration, the airplane always stalls at the same AOA, referred to as the critical AOA. This critical AOA does not change with 1. Weight. 2. Bank angle. 3. Temperature. 4. Density altitude. 5. Center of gravity. An AOA indicator can have several benefits when installed in general aviation aircraft, not the least of which is increased situational awareness. Without an AOA indicator, the AOA is invisible to pilots. These devices measure several parameters simultaneously and determine the current AOA, providing a visual image to the pilot of the current AOA along with representations of the proximity to the critical AOA. Figure 5.42. These devices can give a visual representation of the energy management state of the airplane. The energy state of an airplane is the balance between airspeed, altitude, drag, and thrust and represents how efficiently the airfoil is operating. The more efficiently the airfoil operates, the larger stall margin that is present. With this increased situational awareness pertaining to the energy condition of the airplane, pilots will have information that they need to aid in preventing an LOC scenario resulting from a stall/spin. Additionally, the less energy that is utilized to maintain flight means greater overall efficiency of the airplane, which is typically realized in fuel savings. This equates to a lower operating cost to the pilot. Just as training is required for any system on an aircraft, AOA indicators have training considerations also. A more comprehensive understanding of AOA in general should be the goal of this training, along with the specific operating characteristics and limitations of the installed AOA indicator. Ground and flight instructors should make every attempt to receive training from an instructor knowledgeable about AOA indicators prior to giving instruction pertaining to or in airplanes equipped with AOA indicators. Pilot schools should incorporate training on AOA indicators in their syllabi, whether their training aircraft are equipped with them or not. Installation of AOA indicators not required by type certification in general aviation airplanes has recently been streamlined by the FAA. The FAA established policy in February 2014 pertaining to non-required AOA systems and how they may be installed as a minor alteration, depending upon their installation requirements and operational utilization, and the procedures to take for certification of these installations. For updated information, reference the FAA website at www.faa.gov. While AOA indicators provide a simple visual representation of the current AOA and its proximity to the critical AOA, they are not without their limitations. These limitations should be understood by operators of general aviation airplanes equipped with these devices. End of page 5 to 27. Like advanced automation, such as autopilots and moving maps, the misunderstanding or misuse of the equipment can have disastrous results. Some items which may limit the effectiveness of an AOA indicator are listed below. 1. Calibration techniques. 2. Probes or vanes not being heated. 3. The type of indicator itself. 4. Flap setting. 5. Wing contamination. Pilots of general aviation airplanes equipped with AOA indicators should contact the manufacturer for specific limitations applicable to that installation. Basic propeller principles. The aircraft propeller consists of 2 or more blades and a central hub to which the blades are attached. Each blade of an aircraft propeller is essentially a rotating wing. As a result of their construction, the propeller blades are like airfoils and produce forces that create the thrust to pull, or push, the aircraft through the air. The engine furnishes the power needed to rotate the propeller blades through the air at high speeds, and the propeller transforms the rotary power of the engine into forward thrust. A cross-section of a typical propeller blade is shown in Figure 5.43. This section or blade element is an airfoil comparable to a cross-section of an aircraft wing. One surface of the blade is cambered or curved, similar to the upper surface of an aircraft wing, while the other surface is flat like the bottom surface of a wing. The chord line is an imaginary line drawn through the blade from its leading edge to its trailing edge. As in a wing, the leading edge is the thick edge of the blade that meets the air as the propeller rotates. Blade angle, usually measured in degrees, is the angle between the chord of the blade and the plane of rotation and is measured at a specific point along the length of the blade. Figure 5.44. Because most propellers have a flat blade face, the chord line is often drawn along the face of the propeller blade. Pitch is not blade angle, but because pitch is largely determined by blade angle, the two terms are often used interchangeably. End of page 5 to 28. An increase or decrease in one is usually associated with an increase or decrease in the other. The pitch of a propeller may be designated in inches. A propeller designated as a 74 to 48 would be 74 inches in length and have an effective pitch of 48 inches. The pitch is the distance in inches, which the propeller would screw through the air in one revolution if there were no slippage. When specifying a fixed pitch propeller for a new type of aircraft, the manufacturer usually selects one with a pitch that operates efficiently at the expected cruising speed of the aircraft. Every fixed-pitch propeller must be a compromise because it can be efficient at only a given combination of airspeed and revolutions per minute, RPM. Pilots cannot change this combination in flight. When the aircraft is at rest on the ground with the engine operating, or moving slowly at the beginning of takeoff, the propeller efficiency is very low because the propeller is restrained from advancing with sufficient speed to permit its fixed-pitch blades to reach their full efficiency. In this situation, each propeller blade is turning through the air at an AOA that produces relatively little thrust for the amount of power required to turn it. To understand the action of a propeller, consider first its motion, which is both rotational and forward. As shown by the vectors of propeller forces in Figure 5.44, Each section of a propeller blade moves downward and forward. The angle at which this air, relative wind, strikes the propeller blade is its AOA. The air deflection produced by this angle causes the dynamic pressure at the engine side of the propeller blade to be greater than atmospheric pressure, thus creating thrust. The shape of the blade also creates thrust because it is cambered like the airfoil shape of a wing. As the air flows past the propeller, the pressure on one side is less than that on the other. As in a wing, a reaction force is produced in the direction of the lesser pressure. The airflow over the wing has less pressure, and the force, lift, is upward. In the case of the propeller, which is mounted in a vertical instead of a horizontal plane, the area of decreased pressure is in front of the propeller, and the force, thrust, is in a forward direction. Aerodynamically, thrust is the result of the propeller shape and the AOA of the blade. Thrust can be considered also in terms of the mass of air handled by the propeller. In these terms, thrust equals mass of air handled multiplied by slipstream velocity minus velocity of the aircraft. The power expended in producing thrust depends on the rate of air mass movement. On average, thrust constitutes approximately 80% of the torque, total horsepower absorbed by the propeller. The other 20% is lost in friction and slippage. For any speed of rotation, the horsepower absorbed by the propeller balances the horsepower delivered by the engine. For any single revolution of the propeller, the amount of air handled depends on the blade angle, which determines how big a bite of air the propeller takes. Thus, the blade angle is an excellent means of adjusting the load on the propeller to control the engine RPM. The blade angle is also an excellent method of adjusting the AOA of the propeller. On constant speed propellers, the blade angle must be adjusted to provide the most efficient AOA at all engine and aircraft speeds. Lift versus drag curves, which are drawn for propellers as well as wings, indicate that the most efficient AOA is small, varying from +2 degrees to +4 degrees. The actual blade angle necessary to maintain this small AOA varies with the forward speed of the aircraft. Fixed pitch and ground adjustable propellers are designed for best efficiency at one rotation and forward speed. They are designed for a given aircraft and engine combination. A propeller may be used that provides the maximum efficiency for takeoff, climb, cruise, or high-speed flight. Any change in these conditions results in lowering the efficiency of both the propeller and the engine. Since the efficiency of any machine is the ratio of the useful power output to the actual power input, propeller efficiency is the ratio of thrust horsepower to brake horsepower. Propeller efficiency varies from 50 to 87%, depending on how much the propeller slips. Propeller slip is the difference between the geometric pitch of the propeller and its effective pitch. End of page 5 to 29. Figure 5.45. Geometric pitch is the theoretical distance a propeller should advance in one revolution. Effective pitch is the distance it actually advances. Thus, geometric or theoretical pitch is based on no slippage, but actual or effective pitch includes propeller slippage in the air. The reason a propeller is twisted is that the outer parts of the propeller blades, like all things that turn about a central point, travel faster than the portions near the hub. Figure 5.46. If the blades had the same geometric pitch throughout their lengths, portions near the hub could have negative AOAs while the propeller tips would be stalled at cruise speed. Twisting or variations in the geometric pitch of the blades permits the propeller to operate with a relatively constant AOA along its length when in cruising flight. Propeller blades are twisted to change the blade angle in proportion to the differences in speed of rotation along the length of the propeller, keeping thrust more nearly equalized along this length. Usually 1 degree to 4 degrees provides the most efficient lift/drag ratio, but in flight the propeller AOA of a fixed-pitch propeller varies, normally from 0 degrees to 15 degrees. This variation is caused by changes in the relative airstream, which in turn results from changes in aircraft speed. Thus, propeller AOA is the product of two motions: propeller rotation about its axis and its forward motion. A constant speed propeller automatically keeps the blade angle adjusted for maximum efficiency for most conditions encountered in flight. During takeoff, when maximum power and thrust are required, the constant speed propeller is at a low propeller blade angle or pitch. The low blade angle keeps the AOA small and efficient with respect to the relative wind. At the same time, it allows the propeller to handle a smaller mass of air per revolution. This light load allows the engine to turn at high RPM and to convert the maximum amount of fuel into heat energy in a given time. The high RPM also creates maximum thrust because, although the mass of air handled per revolution is small, the RPM and slipstream velocity are high, and with the low aircraft speed, there is maximum thrust. After liftoff, as the speed of the aircraft increases, the constant speed propeller automatically changes to a higher angle, or pitch. Again, a higher blade angle keeps the AOA small and efficient with respect to the relative wind. The higher blade angle increases the mass of air handled per revolution. This decreases the engine RPM, reducing fuel consumption and engine wear, and keeps thrust at a maximum. After the takeoff climb is established in an aircraft having a controllable pitch propeller, the pilot reduces the power output of the engine to climb power by first decreasing the manifold pressure and then increasing the blade angle to lower the RPM. At cruising altitude, when the aircraft is in level flight and less power is required than is used in takeoff or climb, the pilot again reduces engine power by reducing the manifold pressure and then increasing the blade angle to decrease the RPM. Again, this provides a torque requirement to match the reduced engine power. Although the mass of air handled per revolution is greater, it is more than offset by a decrease in slipstream velocity and an increase in airspeed. The AOA is still small because the blade angle has been increased with an increase in airspeed. Torque and P factor. To the pilot, torque, the left turning tendency of the airplane, is made up of four elements that cause or produce a twisting or rotating motion around at least one of the airplane's three axes. These four elements are: 1. Torque reaction from engine and propeller. End of page 5 to 30. 2. Corkscrewing effect of the slipstream. 3. Gyroscopic action of the propeller. 4. Asymmetric loading of the propeller, P factor. Torque reaction. Torque reaction involves Newton's third law of physics: for every action, there is an equal and opposite reaction. As applied to the aircraft, this means that as the internal engine parts and propeller are revolving in one direction, an equal force is trying to rotate the aircraft in the opposite direction. Figure 5.47. When the aircraft is airborne, this force is acting around the longitudinal axis, tending to make the aircraft roll. To compensate for roll tendency, some of the older aircraft are rigged in a manner to create more lift on the wing that is being forced downward. The more modern aircraft are designed with the engine offset to counteract this effect of torque. Note, most United States-built aircraft engines rotate the propeller clockwise, as viewed from the pilot's seat. The discussion here is with reference to those engines. Generally, the compensating factors are permanently set so that they compensate for this force at cruising speed, since most of the aircraft's operating time is at that speed. However, aileron trim tabs permit further adjustment for other speeds. When the aircraft's wheels are on the ground during the takeoff roll, an additional turning moment around the vertical axis is induced by torque reaction. As the left side of the aircraft is being forced down by torque reaction, more weight is being placed on the left main landing gear. This results in more ground friction, or drag, on the left tire than on the right, causing a further turning moment to the left. The magnitude of this moment is dependent on many variables. Some of these variables are: 1. Size and horsepower of engine. 2. Size of propeller and the RPM. 3. Size of the aircraft. 4. Condition of the ground surface. This yawing moment on the takeoff roll is corrected by the pilot's proper use of the rudder or rudder trim. Corkscrew effect. The high-speed rotation of an aircraft propeller gives a corkscrew or spiraling rotation to the slipstream. At high propeller speeds and low forward speed, as in the takeoffs and approaches to power on stalls, this spiraling rotation is very compact and exerts a strong sideward force on the aircraft's vertical tail surface. Figure 5.48. When this spiraling slipstream strikes the vertical fin, it causes a yawing moment about the aircraft's vertical axis. The more compact the spiral, the more prominent this force is. As the forward speed increases, however, the spiral elongates and becomes less effective. The corkscrew flow of the slipstream also causes a rolling moment around the longitudinal axis. Note that this rolling moment caused by the corkscrew flow of the slipstream is to the right, while the yawing moment caused by torque reaction is to the left. In effect, one may be counteracting the other. However, these forces vary greatly, and it is the pilot's responsibility to apply proper corrective action by use of the flight controls at all times. These forces must be counteracted regardless of which is the most prominent at the time. Gyroscopic action. Before the gyroscopic effects of the propeller can be understood, it is necessary to understand the basic principle of a gyroscope. All practical applications of the gyroscope are based upon two fundamental properties of gyroscopic action: rigidity in space and precession. The one of interest for this discussion is precession. Precession is the resultant action, or deflection, of a spinning rotor when a deflecting force is applied to its rim. As can be seen in Figure 5.49, when a force is applied, the resulting force takes effect 90 degrees ahead of and in the direction of rotation. The rotating propeller of an airplane makes a very good gyroscope and thus has similar properties. End of page 5 to 31. Anytime a force is applied to deflect the propeller out of its plane of rotation, the resulting force is 90 degrees ahead of and in the direction of rotation and in the direction of application, causing a pitching moment, a yawing moment, or a combination of the two depending upon the point at which the force was applied. This element of torque effect has always been associated with and considered more prominent in tailwheel type aircraft and most often occurs when the tail is being raised during the takeoff roll. Figure 5.50. This change in pitch attitude has the same effect as applying a force to the top of the propeller's plane of rotation. The resultant force acting 90 degrees ahead causes a yawing moment to the left around the vertical axis. The magnitude of this moment depends on several variables, one of which is the abruptness with which the tail applied force is raised, amount of force applied. However, precession, or gyroscopic action, occurs when a force is applied to any point on the rim of the propeller's plane of rotation. The resultant force will still be 90 degrees from the point of application in the direction of rotation. Depending on where the force is applied, the airplane is caused to yaw left or right, to pitch up or down, or a combination of pitching and yawing. It can be said that, as a result of gyroscopic action, any yawing around the vertical axis results in a pitching moment, and any pitching around the lateral axis results in a yawing moment. To correct for the effect of gyroscopic action, it is necessary for the pilot to properly use elevator and rudder to prevent undesired pitching and yawing. Asymmetric loading, P-factor. When an aircraft is flying with a high AOA, the bite of the downward moving blade is greater than the bite of the upward moving blade. This moves the center of thrust to the right of the prop disc area, causing a yawing moment toward the left around the vertical axis. Proving this explanation is complex because it would be necessary to work wind vector problems on each blade while considering both the AOA of the aircraft and the AOA of each blade. This asymmetric loading is caused by the resultant velocity, which is generated by the combination of the velocity of the propeller blade in its plane of rotation and the velocity of the air passing horizontally through the propeller disc. With the aircraft being flown at positive AOAs, the right, viewed from the rear, or downswinging blade, is passing through an area of resultant velocity, which is greater than that affecting the left or upswinging blade. Since the propeller blade is an airfoil, increased velocity means increased lift. The downswinging blade has more lift and tends to pull, yaw, the aircraft's nose to the left. When the aircraft is flying at a high AOA, the downward moving blade has a higher resultant velocity, creating more lift than the upward moving blade. Figure 5.51. This might be easier to visualize if the propeller shaft was mounted perpendicular to the ground, like a helicopter. If there were no air movement at all, except that generated by the propeller itself, identical sections of each blade would have the same airspeed. With air moving horizontally across this vertically mounted propeller, the blade proceeding forward into the flow of air has a higher airspeed than the blade retreating with the airflow. Thus, the blade proceeding into the horizontal airflow is creating more lift, or thrust, moving the center of thrust toward that blade. Visualize rotating the vertically mounted propeller shaft to shallower angles relative to the moving air, as on an aircraft. This unbalanced thrust then becomes proportionally smaller and continues getting smaller until it reaches the value of 0 when the propeller shaft is exactly horizontal in relation to the moving air. The effects of each of these four elements of torque vary in value with changes in flight situations. In one phase of flight, one of these elements may be more prominent than another. In another phase of flight, another element may be more prominent. The relationship of these values to each other varies with different aircraft depending on the airframe, engine, and propeller combinations, as well as other design features. To maintain positive control of the aircraft in all flight conditions, the pilot must apply the flight controls as necessary to compensate for these varying values. End of page 5 to 32. Load factors. In aerodynamics, the maximum load factor, at given bank angle, is a proportion between lift and weight and has a trigonometric relationship. The load factor is measured in GS, acceleration of gravity, a unit of force equal to the force exerted by gravity on a body at rest, and indicates the force to which a body is subjected when it is accelerated. Any force applied to an aircraft to deflect its flight from a straight line produces a stress on its structure. The amount of this force is the load factor. While a course in aerodynamics is not a prerequisite for obtaining a pilot's license, the competent pilot should have a solid understanding of the forces that act on the aircraft, the advantageous use of these forces, and the operating limitations of the aircraft being flown. For example, a load factor of 3 means the total load on an aircraft structure is 3 times its weight. Since load factors are expressed in terms of GS, a load factor of may 3rd be spoken of as 3 GS, or a load factor of 4 is 4 GS. If an aircraft is pulled up from a dive, subjecting the pilot to 3 GS, he or she would be pressed down into the seat with a force equal to 3 times his or her weight. Since modern aircraft operate at significantly higher speeds than older aircraft, increasing the potential for large load factors, this effect has become a primary consideration in the design of the structure of all aircraft. With the structural design of aircraft planned to withstand only a certain amount of overload, a knowledge of load factors has become essential for all pilots. Load factors are important for 2 reasons. 1. It is possible for a pilot to impose a dangerous overload on the aircraft structures. 2. An increased load factor increases the stalling speed and makes stalls possible at seemingly safe flight speeds. Load factors in aircraft design. The answer to the question, how strong should an aircraft be, is determined largely by the use to which the aircraft is subjected. This is a difficult problem because the maximum possible loads are much too high for use in efficient design. It is true that any pilot can make a very hard landing or an extremely sharp pull-up from a dive, which would result in abnormal loads. However, such extremely abnormal loads must be dismissed somewhat if aircraft are built that take off quickly, land slowly, and carry worthwhile payloads. The problem of load factors in aircraft design becomes how to determine the highest load factors that can be expected in normal operation under various operational situations. These load factors are called limit load factors. For reasons of safety, it is required that the aircraft be designed to withstand these load factors without any structural damage. Although the Code of Federal Regulations, CFR, requires the aircraft structure be capable of supporting 1 1/2 times these limit load factors without failure, it is accepted that parts of the aircraft may bend or twist under these loads and that some structural damage may occur. This 1.5 load limit factor is called the factor of safety and provides, to some extent, for loads higher than those expected under normal and reasonable operation. This strength reserve is not something that pilots should willfully abuse, rather, it is there for protection when encountering unexpected conditions. The above considerations apply to all loading conditions, whether they be due to gusts, maneuvers, or landings. The gust load factor requirements now in effect are substantially the same as those that have been in existence for years. Hundreds of thousands of operational hours have proven them adequate for safety. Since the pilot has little control over gust load factors, except to reduce the aircraft's speed when rough air is encountered, the gust loading requirements are substantially the same for most general aviation-type aircraft regardless of their operational use. Generally, the gust load factors control the design of aircraft which are intended for strictly non-acrobatic usage. An entirely different situation exists in aircraft design with maneuvering load factors. It is necessary to discuss this matter separately with respect to 1. Aircraft designed in accordance with the category system, i.e., normal, utility, acrobatic, and 2. Older designs built according to requirements that did not provide for operational categories. Aircraft designed under the category system are readily identified by a placard in the flight deck, which states the operational category, or categories, in which the aircraft is certificated. End of page 5 to 33. The maximum safe load factors, limit load factors, specified for aircraft in the various categories are: Category Limit Load Factor. Normal 1 3.8 to -1.52. Utility, mild acrobatics, 4.4 to -1.76 including spins. Acrobatics 6.0 to -3.001. For aircraft with gross weight of more than 4,000 pounds, the limit load factor is reduced. To the limit loads given above, a safety factor of 50% is added. There is an upward graduation in load factor with the increasing severity of maneuvers. The category system provides for maximum utility of an aircraft. If normal operation alone is intended, the required load factor, and consequently the weight of the aircraft, is less than if the aircraft is to be employed in training or acrobatic maneuvers, as they result in higher maneuvering loads. Aircraft that do not have the category placard are designs that were constructed under earlier engineering requirements in which no operational restrictions were specifically given to the pilots. For aircraft of this type, up to weights of about 4,000 pounds, the required strength is comparable to present-day utility category aircraft, and the same types of operation are permissible. For aircraft of this type over 4,000 pounds, the load factors decrease with weight. These aircraft should be regarded as being comparable to the normal category aircraft designed under the category system, and they should be operated accordingly. Load factors in